So one can load the data in SPSS. One will obtain the second stage correct estimate, but one does not know the extent to which the model is valid and how strong the instruments are. Now, you can do this by hand. It's in my chapter, Causality and Endogeneity, but I don't suggest you do it. I suggest that one immediately considers adopting either R or Starter or perhaps SAS, SAS. I have a little video. I gave an interview to Starter a couple of months ago, and they asked me when I adopted SPS, when I started using Starter, and I was a diehard SPSS user. I know SPSS very, very well, and I can program it pretty well. And I was teaching experimental statistics with SPSS up until 2006 or 5, and then I stopped using it because I noticed it had some severe limitations. So as a joke, whenever psychology students take my causal analysis class, I tell them, you know, SPSS can do the job. It's like, you know, racing in Formula 1 on a tricycle. You know, you can finish, but it's going to be very painful and it will take a lot longer. So, you know, stuff that took me 30 or 40 lines of code to program in SPSS, I can program in 3 or 4 lines in Starter. So it's just got a lot more modules. It's more efficient. It's more user-friendly. It's much easier to program. So the reason why I teach in Starter and not R, it's because it's easier for students to learn the programming language. R is not difficult. It's just a bit more clunky. And so, you know, if one has the resources to be able to use Starter, I would suggest it. So like I said, again, one can do everything in SPSS, but it requires programming and it requires some stuff to be done by hand. You know, you can easily do a lot of the stuff also on Excel. So, you know, even Excel is fine. I'll even show you today, we can do multi-level modeling in Excel and people will be like, what? Very easy. The regression, I'll show you. So
John, quick question regarding that. So thanks for the response regarding SPSS. But SEM packages, if we do a maximum likelihood type of estimation, all we have to do is let the errors of the mediator and outcome variable correlate. But how do we know whether, like, how can we answer those questions that you just put forth that the SPSS cannot easily answer?
Okay, so let me quickly show you. Let me just share my other screen. So how you would do it in SEM, huh? Okay.
Like essentially, if I run the model that I just specified.
Yeah, you can run it in SEM.
I won't know whether the exogenous variable is sufficiently related to the mediator.
I'll show you now. 1 second, I just need to share my screen on this computer. A host has disabled screen sharing. Can I share screens on my backup computer, Genevieve? Or maybe I can make myself co-host.
Yes. Sorry about that. Yes.
No problem.
Co-host. Okay.
So let me share my screen. Not the starter, the starter. Okay, so here's so this is in the Google Docs. So basically, this is a model where we are predicting M from X1, X2, and the interaction of X1, X2. I need to put X1 here. So what's going to be missing is stat endog. So the endogeneity test is going to be missing. This you can do by hand, and I show it in my book chapter, Endogeneity and Causality. Literally, you can do it by hand. SPSS has all the things to get the calculations. You just have to construct some auxiliary regressions, and I'll show you how to do that. Stat overrid, so it does not have this test either. Again, you can do it by hand. I'll show you exactly how to do it. You need to do an auxiliary regression, get the R squared, multiply it by the sample size, and then look at the distribution of the chi-squared. So it doesn't have these things, nor does it have this stat first. It's the stat first tells you how strong your F statistic is in the first stage and whether it is above or below the critical thresholds for the bias in the estimator. So this, it doesn't have it either. Okay, so this is the problem. Now, if you were to do this in SEM, you would get everything except the last part, and you can kind of do it manually. So in SEM, we would specify, if you're using Amos or anything else, we would say, you know, M depending on X1, X2, and the interaction. Okay. And then we correlate the disturbances. You do that in drawing, right? With Amos. Are most people here Amos users, M+, Lisrel, or EQS?
I don't know. I can't speak for everyone. I use Amos, but I'm sick and tired of the user interface.
Okay. So, you know, any one of these things can do what I'm showing you now. So the first thing is you will get an over-identification test if the model is over-identified. So this model has 2 degrees of freedom. So we know that this model is correctly specified. You do get the endogeneity test. This is the covariance of E with Y. So, I mean, this is just, if you were to do it, if you were to do this manually, it's the Wald test for the disturbance. So if I did test this equals 0, this test is exactly the same as the test I show you up here. Except this is giving a Z statistics. It's 467. This is giving me a chi-squared statistics. So if I were to take the square root of this, I should get 467. There you go, 466, 467. Okay. So basically the Wald test for this thing equals 0 is the Hausman endogeneity test. Now, what you don't have in SEM is this. You don't have the F statistic of the first stage, but you can actually recover it by doing a simultaneous test of all these coefficients equal 0. So this is basically the chi-square test. If anyone uses M+ in here, what you would do is create a Wald test for all these parameters equal 0. So this is a 3 degree of freedom test. If you divide 53 by 3, that's F squared distributed. So this 53.10 divided by 3, and you get 17.7. Okay, now if we go back to the document I showed you before, this document, look at that. You see that F statistic? 17.97. That's approximately equal to the chi-squared test you're going to get for the 3 coefficients in the M equation equals 0. So that's a Wald test. You can do that in Amos. You can label those 3 parameters and test are those 3 parameters simultaneously different from 0. Okay, so you know that that value is bigger than 10, but still you don't have the the comparisons of stock and Yogo that I showed you before. But all this is done automatically in R and in Starter. Okay, so let me just go back to sharing my screen. Excuse me. Share my screen. Sorry, my computer's just given up. I can't share the screen for a moment. It's just taking a moment. So everything that I showed you, you can do in SEM. You just have to do a few things by hand or construct the test by hand in Amos. Now, Amos has one small problem, which I'm going to show you today. So everything that I'm going to show you today on panel, Amos and SPSS have a bit of a problem. You can get everything in mixed, in the mixed command in SPSS. But if you want to use a least squares estimator to do multi-level modeling, and it's possible to use a least squares estimator, you need a cluster robust estimate of the variance, and Amos doesn't have that, and nor does the regression command of SPSS have that. So that's a limitation. HLM does have that, but as I'll show you today, you don't really need to use HLM. You can use R or Starter. even Excel to do whatever you want to do, as long as you can make correction on the standard errors. Okay. So let me just stop there for a sec and just see if there are any questions about that.
And the other question we had on the doc was about any typical instrument variables.
Yeah.
I know
okay.
you referenced the paper you mentioned yesterday, Sir John's, and one of your chapters,
Yeah.
I think.
Okay. Yeah, I'll do that in a sec. Sorry, let me
Okay,
just do
sure.
one more thing, just to make sure that everyone understands what I just did in here. So when we did this in SEM, we specified this, okay? And basically the test that you need to do to get the first stage F statistic is you need to test beta 1 equals 0, beta 2 equals 0, and beta 3 equals 0. You're going to get a chi-squared statistic here with some degrees of freedom. If you take the chi-squared, divide by the degree of freedom, this is F squared distributed, okay? So that's what you need to do over there, Laurent. So you can label these parameters in AMOS and then do a test. Are these three different from 0? You can do this a WAL test. So this is basically a WAL test, and M+ can do it as well. Okay.
Can I be a little bit of a dodo here? Can you remind me? I just want to make sure that I articulate my question as clearly as possible. So when you said the first stage, right, the being able to test the getting the F value of the first stage, remind me why that is so important.
It's important because we want to make sure that our instruments are strong. Okay, so we need to make sure that these things are strongly related to M.
Because
remember the diagram? Yeah. So you remember that the formula for the IV estimator is covariance instruments with Y divided covariance instruments with M. So the numerator has to be defined, okay? And the denominator has to be defined. If you don't have a strong correlation of these guys with that, this goes to 0, and then you can't you get a singular matrix. So you remember also when I did the Venn diagrams, you remember that?
Yep.
So I said X must be strongly related to M in the, if it's not, we're not gonna get good estimates. So the closer that this denominator goes to 0, the more noisy your estimator is going to be. You're going to get massive amount of noise. So that's the problem. Okay.
Okay, that helps. That helps.
And then to answer the second question, where to get instruments? The best instruments are the ones you exogenously manipulate. So if you can do it in the lab or in a field experiment, that's the best. You are guaranteed your instrument is exogenous. If you don't have the liberty or the luxury to do a manipulation, then some things do exist naturally that can be used as instrumental variables. And I show that in my paper on causal claims. So for example, if there hasn't been selection on IQ could serve as an instrumental variable. Why? My IQ will not change as a function of anything that I might predict in the model. If I'm the boss of AJ, if AJ works hard or not for me, that's not going to make my IQ go up or down. My age is exogenous. My sex is exogenous. So things that are fixed traits in adulthood are pretty much exogenous. They're not going to change very much as a function of something in the system. My testosterone level my baseline is generally exogenous. So, those are the kinds of things we can think of, fixed traits that there's been no selection on in the model. So for example, if we have a sexist environment and we take more men than women, we can't use being male or female or non-binary as an instrument because there's been selection on that. So it's not random, okay?
How do you feel about personality traits?
I think personality is largely exogenous by adulthood because about between 40 to 60% of heritability in Big Five is due to genes, and it's kind of fixed. So of course personality can change over time, and people get more mellow as they get older. But I'm not going to all of a sudden become less extroverted because AJ works harder or less hard. Now, if AJ is psychotic and he freaks me out and every day scares me, he might make me more emotional at work. Okay, so he might be able to change my personality, but that's a very extreme situation. So yeah, I would assume that most personality factors are reasonably stable. Okay.
Okay, that's very helpful. Thank you.
Thank you.
And then we were going to see if there are any questions from participants. So if anyone wants to raise their hand and has anything outstanding from yesterday or any follow-up questions.
Okay.
John, a quick follow-up regarding the use of R. Yeah. I think that's probably quite tantalizing for at least some people because it's rather inexpensive. Now with R, I would be a complete neophyte, for instance, with respect to using R. Does it come with, like, to what extent is there already some type of I shouldn't say cookie cutter solution, but essentially a pre-existing command or set of commands that would allow us to run these models?
Yeah, so R has libraries to run all these models. So like Starter has IV regress, R has an IV estimator. Like Starter has a SEM module, R has Lavan. And actually in SEM, right. R is actually much better than Starter. So, you know, and there are a lot of tutorials on Google and, you know, how to use R for instrumental, you know, just there's plenty of resources. It's quite easy to use, but if you have the money and you can afford the license, I would strongly suggest you get Starter, because Starter puts out lots of educational videos. They do lots of training. There are lots of books on Starter. And there's also the best documentation ever on statistics procedures in the Starter manuals that you get in PDF form. So a lot of the econometrics I did not know and I had to acquire. I actually learned reading the Starter manuals, because not only do they show you how to do it, they show the mathematical derivation behind the method and the formulas, the mathematical formulas, so you can understand what's going on. So that's why I strongly suggest, if you have the money, to use Starter, else use R, no problem.
And a last dumb question, if you will permit me. When you say IV model, IV, are you talking about independent variable?
Instrumental variable.
Oh, thank you.
Yeah, IV estimator, instrument. So two-stage least squares is an IV estimator.
Okay, yeah.
Maximum likelihood can be an IV estimator if specified as such. Yeah.
Okay. Thank you.
No problem.
We have a couple of questions in the chat, John.
I saw that, yeah. Would you please say a few words on what to do if X is observed or measured rather than manipulated? Okay, so if you have a model so who's saying this question? Sylvia, can you open your microphone, please? I need to double check something with you.
Yes, I'm here.
Okay, Sylvia. So is X now personality or something else? Or is X effective state?
The particular model I had in mind was a personality trait. So let's say extroversion leading to an affective state, let's say anxiety leading to particular behavior.
Okay, so when you say X, does X mean personality or does X mean affective state? That's what I'm asking.
X means personality, affective state would be the mediator. Okay,
so this should work. So if X, let me make this red because you can't see that. If this variable here is fixed or is cyclical or is manipulated, it should serve reasonably well as an instrumental variable. So yeah, I can see what you want to do here, and that would work. Okay, that would work, but you need to make sure that the instrument is strong. Okay, and strong is coming from the F statistic in the first stage. Okay, so you need to ensure that it's a strong. So this would work. Okay.
So the case I was thinking of would be the personality trait is our focal variable of interest, as opposed to the instrument that we would use.
No, but in this case, it is an instrument. Because you have the big five here. Imagine you have 5 variables affecting some kind of affective state, which affects their behavior. So these now are specified as instrumental variables.
Okay.
Okay, so what you need to do is again correlate these two disturbances. And you've got to make sure that this model is correctly specified, meaning that the chi-square test is not significant. Okay. If the chi-squared is significant, you need to, for every mediator, you need to have at least one instrument. So at least one instrument must stay in this equation and cannot go into the behavior equation. So imagine if you had 3 instruments, okay? And imagine your chi-square test is significant and your modification index say that it's x3, that's the problem. Then what you can do is you can regress m on x3 and x3 on y, and then leave these 2 instruments in the m equation. You need to have at least one instrument in here because you have one mediator. You need at least one excluded instrument. This is called an included instrument because it's included in the y equation. These are excluded from the y equation. You see that? That's what the causal effect is coming from. That's how we identify the causal effect. All right. So, you know, when you estimate your first model, Sylvia, if you want, you just, you know, send me a little email and say, this is what I've done. Send me your output and ask me if it's done correct. I will provide after sales support for free.
I appreciate that. Thank you very much.
Okay. All right. So let me just recap one small thing because some of you probably have already seen this. So if we have a variable here, which I'm going to call x, and if this variable is measured and is not exogenous, if you want to estimate the effect of x on y, then you better get some instrumental variable to purge the endogeneity of x from y. As soon as we're doing instrumental variable estimation, we are actually testing a mediation model, okay? Sometimes we're interested in gamma 1 times beta 1. Sometimes we're just interested in beta 1. We are interested in the causal effect of charisma on y, okay? If we can't manipulate charisma and we measure it, then we better have an instrumental variable. What is that? IQ big 5, or is it a manipulation training? So when we do IV estimation, we can test mediation effects, or we can test second stage effects, or we can test reduced form effects. Okay? We can do any of these 3 things. We can look at the effect of x on y, we can look at the mediation effect, or we can look at the reduced form. Any of the 3, depends on the question you're asking. So basically that's what we did yesterday. And what I tried to explain yesterday, if that x is measured, you cannot use the usual mediation methods. You need to use IV. And as long as you have an IV estimator, you can do any of these 3 things. And it works even if you don't have endogeneity, which is what I showed Jason yesterday. All right. Okay, so let's begin. From Duke, hi John, can we use instrument variable for mediate M if we have a direct link from X to Y? I don't understand the question. Duke, can you please open your mic and tell me what you mean, please?
Hi John, can you hear me?
Yes.
Oh, so I think the first question I planned to ask you before is like we have an independent variable, right? X, a mediator M, and a dependent variable Y.
Yeah.
So yeah, so I'm thinking about like the model when there's a direct link from X to Y, but I think you answered my question already by using the reduced form.
Yeah, you can do the reduced form.
Yes.
That's possible, but you can't do this. You can't put a direct link in there from X to Y when you're doing this, because this model is not identified. It's got -1 degree of freedom. It can't be identified. This can only be estimated if you kill the correlation of the covariance. So you got to kill this, and then this reverts to OLS, and this is Preacher and Hayes, the model, which is wrong.
I see.
Okay,
Thank you so much. Yeah.
No problem.
I used a lot of yes before, but now I see. Yeah. I got a question about endogeneity from the reviewer, so I tried to solve that question. That's why I stumbled about instrument variable before. But like I said, there's a lot of questions left. Thank you so much for doing this.
No problem at all. And let me just say something. In 10 years from now, I think every major journal in management and psychology is going to know about endogeneity. It's just taking time. Right now, Strategic Management Journal, it's on the radar for them. Journal of Business Venturing, it's on the radar for them. Journal of Management, they're starting to worry about it. The journals where they're not so worried about it yet is JAP and AMJ, but even in there, from time to time, you see that this is mentioned, okay? So it's really going to be a very prevalent thing very, very soon, okay? All right, so let's talk about endogeneity now in panel data. So given the very extensive introduction I gave yesterday, today's mathematical derivations will go much faster because it's exactly the same problem as I showed you yesterday. So mediation model and multi-level models, I think a lot of you already know about them. It has to do with data that varies on multiple levels of analysis, for example, individuals in firms. And there are two different traditions in working with multi-level models, the econometrics and sociometrics, sociological perspective, and the education, management, and psychology literatures, okay? These two literatures have been developed in parallel and they haven't talked to each other, and there's a lot of confusion about what each of the literatures is doing. As you can imagine, the econometrics approach is much more concerned about endogeneity. The other approach has not been, but now is more and more concerned about it. In part of the readings, I sent you a paper by McNeish in Psych Methods. There's also a paper by Paul Bleasy that just came out recently in the Journal of Management, and they argue and cite quite extensively the work that I've done on multi-level models to suggest that it's really important you check whether your multi-level model has endogeneity. So, now that the Psych Methods paper has come out on it, I think this is something that's going to be also on the radar of psychologists and management scholars. So let's quickly define by what we mean in these models. Sorry, I was talking about the confusion. So this literature is technical. It's very fragmented. This is the paper that I was suggesting by Paul Bleasy. So he's the editor of ORM. So please take a look at this paper because it just came out now. And the McNeish and Kelly paper, that's the one I was talking about in Psych Methods. So everything I say today is exactly what they are saying as well. And it's exactly what we published in our 2010 paper. And it's exactly what we said in the ORM paper, where we just took it a few steps further to show the importance of testing for endogeneity. So many researchers would benefit to know how to appropriately estimate these models and to tackle the endogeneity problem, because there's a very particular form of endogeneity in hierarchical models. As I'm going to show you, 1 in 2 papers ignores the standard assumption that HLM does when you estimate an HLM model. And the biggest shock is that I'm going to show you, you can estimate multi-level models in OLS. Okay, so this is, I think, the most interesting thing, because in most of the technical literature, you're going to read OLS can't do this, OLS can't do this. I'll show you that it can do it as long as you set up the model correctly. We need to get the terminology correct in the beginning. So most of you have heard of HLM models or random intercept models. Okay, so I'm going to just focus on a 2-level multi-level model, with the special case of which is called a random intercept model. I'm going to define these terms in a few minutes. Most of you probably have heard these already. So we're going to talk about I being the lower level and J being the higher level. So I is level 1 and J is level 2, or J is often called the cluster. And what we care about is how Xij affects Yij. So usually what people are interested is what's called the within effect. So in micro research, in my field in leadership, for example, a common scenario is we have leaders at level 2, that's J, and they supervise many subordinates, that's I, okay? And we're interested in something that the leader does and how it affects the followers, okay? So that's one scenario. Another scenario could be firm I nested in industry J. So the industry is level 2, firm is level 1. Or in the case of panel data, we may study a firm level 2, and over time, those are the I level variables. So if I study individuals, J, and I measure their productivity or their weight or their attitude over time, then J level 2 is the individual and I is the measurement period of the individual. Okay. Now, what's important here, and here I really need you to pay attention and not get confused with what is said in the education and in the management literatures, is the notion of fixed effect. Okay. So when I say, or when econometrics says fixed effects, a fixed effect is a constant effect due to the higher level entity that we may or may not be able to observe. So for example, leaders working in a particular organization have something in common as compared to leaders working in another organization, which may be correlated with Y, but also with individual level characteristics of the leader. Or second example, individuals studied over time may have something about them that correlates with Y as well as with individual level regressors. So for example, over time, if I'm studying how effective a leader is, and imagine I measure the leader's charisma, at time 1, the leader gives a speech and I measure how productive the followers are the week later. Or I have a study on governors. We measure a governor's speech, how charismatic it is. And then when if people socially distance 1 day after or 7 days after, and I repeatedly measure the governor over time, and I repeatedly measure the Y variable over time, here's a question to you. Perhaps the speech of the governor has an effect on whether people socially distance. But what is it about governors that make governors different, which may affect whether they are charismatic or whether people socially distance and listen to them? Can you give me some examples? Anyone? What individual differences may governor have that makes governors different, which may affect their charisma and also whether people follow them? Gender, I agree. You see, this is so linked to what we said yesterday. Anything else? Sex, yeah, sex, gender. Ah, Jason is here. Hi, Jason. Attraction, how attractive they are. Yes, absolutely. That may affect. Okay, again, extroversion, intelligence, all those individual difference factors we said. Okay, so those things may affect X when we measure X and may affect Y. All right. So this is what we call fixed effect. Fixed effect is the sum total of J level variables that will affect X and will affect Y. So this is just a simple endogeneity problem. So suppose we have panel data for individual I nested in level 2J. So the fixed effect is what now I will call in this case UJ. There's something about the individual that affects X and Y, and we're going to call this UJ. It's a U meaning it's a latent variable, it's unobserved, and it's at the J level. So there's a shock, a common shock that affects each individual leader different, which may correlate with X and may correlate with Y, okay? And usually it does correlate. Now, if we ignore UJ, it means that we will not model it, or we will assume that it does nothing in the model. So if we just throw it away and we don't care about it, uj is going to go in the v term. Okay, and just like we did yesterday, we can ask the question, when is beta 1 going to equal to gamma 1 in here? Okay, and as we said yesterday, and I think Laurent answered it, if this common shock is not related to x, or if this common shock is not related to y, then we can throw it away. But if uj correlates with x, and if gamma 2 is not equal to 0, and if we don't model uj properly, we're going to have an endogeneity problem. Now, this case, this variable is unobserved, but I'm going to show you we can actually model it correctly using an econometrics approach. So just like we did yesterday, suppose that uj correlates with x, and here's the other thing. There are endogeneity tests, just like the Hausman endogeneity test I showed you yesterday, which we can test whether the Preacher and Hayes method works. There's a Hausman test here to see whether the HLM model we have specified works. So if uj correlates with xij, irrespective of the direction, we derive equation A3. Just like yesterday, what we're going to do is we're going to substitute, instead of uj, we're going to substitute that back into equation 1a. So we're going to put this in here instead of u. And when we multiply it, we see that this is what happens in V. V includes the effect of u on y, the effect of u on x, and these parameters. So if we rearrange again, just like we did yesterday, this ugly equation, what we see is that we get exactly the same derivation that we did yesterday, except here the omitted variable is uj. So the effect of x on y is going to depend on x's effect on y, but x's correlation with uj and uj's effect on y. So we need to include this omitted variable called uj if this omitted variable uj is correlated with x or with y. All right. So we have exactly the same problem that I showed you yesterday. The covariance between x and y is going to depend on gamma 1, but also gamma 2 omega 1, which is not going to equal gamma 1 unless gamma 2 or omega 1 are 0. So it's exactly the same problem as yesterday. All right. So you've seen these things before if you've done a class on HLM. Using the basic notation of Rowden, Bush, and Brick, we can see that we have a level 1 and we have level 2. So basically, this here is an outcome in these equations. Okay, so the intercept depends on the common shock, and the parameter beta 1 depends on the common shock. So uj affects both the intercept and the parameter that we are trying to estimate. Okay, so the regression coefficients beta and gamma are fixed parameters. Now, sometimes, and this is where the confusion comes, in the education, in the management and psychology literature, instead of calling these fixed parameters, guess what? They call it fixed effects. And that's not what fixed effects is in econometrics. So please don't confuse fixed parameters with fixed effects. Fixed effects is something else, and I'm going to show you this in a few minutes. So equation 1a can be re-expressed by substituting for beta 0 and substituting for beta 1 in the y equation, and this is what we get. So this is the general equation for a multi-level model. We have a fixed part, and this is not a fixed effect. It's just called the fixed part because these parameters are fixed. And then we have a random part. Why? Because these are random parameters. Okay, we have a random disturbance at the ij level. We have a random disturbance at the j level, and then we have this random term over here. So the fixed part only contains fixed coefficients and gives the regression line, not to be confused with the fixed effects. And the random part contains random effects indicating how observations vary around the line. Now, we're going to strip this model down to the simplest form, and only focus on the random intercept model, where the slopes beta 1j do not vary. Okay, so we're going to drop this. So we're going to assume that beta 1 do not vary, that they are fixed. And so we're going to drop this ugly term over here. Okay, this captures how what's called a random coefficients model. And we're going to look at two different versions of how these models are estimated in econometrics and usually in psychometrics. Okay, so this is the random intercepts model, where uj is treated as a random variable. Okay, and this is the fixed effect model, where we don't assume it's a random variable, but we move it to the fixed part and we model it explicitly. Now, let me just stop for a moment and ask you all a question. Anyone can answer this. When we have a model like this, and if we assume we have two random parameters that we're going to model, what assumption are we making about these disturbances? What do we assume about these disturbances? So whenever there's a disturbance in a model, what assumption do we make? The typical assumption. Anyone? It's normally distributed. That's the first assumption. And the second assumption, it's uncorrelated. Very good. So we assume that the correlation between U and X is 0, and the correlation between E and X is 0. So these are the standard assumptions that we make, whether we use maximum likelihood, restricted maximum likelihood, or OLS. This is a standard assumption we make. Now, here's the question. Laurent, since you answered uncorrelated, may I pick on you, if you don't mind opening your mic?
No problem.
Now, if UJ captures the sum total of unobserved effects at the leader level, my intelligence, my good looks, my everything, and if I measure how my charisma varies over time in Xij and how my charisma predicts subordinate satisfaction, is it possible that my charisma may depend on my intelligence, may depend on a whole bunch of things which are captured in UJ? And is it a heroic assumption to make that UJ is uncorrelated to X?
Yes.
It's a heroic assumption. Okay, I'm glad you agree with that. Now, here's the thing. We can actually move UJ into the fixed part. But you might say to me, but how can we do that if we don't know what these things are? I'm going to show you that, okay? So the model in equation 3a makes more assumptions than the model in equation 3b. This makes only one assumption. Do you agree, Laurent? This makes one assumption. This makes two assumptions.
Mm-hmm.
Now, normally we would like to use models that make fewer assumptions, because fewer assumptions means it's got fewer ways to go wrong. Okay. So in the random effects model, UJ is random intercept to modeling unobserved between cluster variation. So what makes leaders different? Which affects the intercept of Y. And that's the sum total of things at the leader level. In the fixed effect model, the between cluster variation is assigned to the fixed part represented by AJ. And we model these explicitly using dummy variables. I'm going to show you that in a minute. In the random effects approach, we just model the variance of the UJ term, but we do not specifically estimate the differences in the values. So the random effects model makes an additional assumption that covariance X UJ is 0, and that's called the random effects assumption. Now, the fixed effect approach does not require this restricted assumption, because we move UJ into the fixed part of the model and we estimated explicitly case values for each leader in the data set. Now, there are two limitations with this approach, but these limitations are straw man limitations. Number one, it's slightly less efficient. Now, as long as your sample is reasonably large, this is going to be completely irrelevant. Okay, so the efficiency assumption is totally irrelevant. Here's the problem, and it's not really a problem because I'm going to show you how we can work around this. We cannot estimate a fixed effects model if we are interested in level 2 variables. So for example, Laurent, you might be interested actually in modeling the leader's IQ, the leader's sex, the leader's age, the leader's personality. You might want to include these in the model at the J level. So these things don't vary within leader, they're constant. Now, if these things don't vary within leader, we cannot include dummy variables because they're completely collinear with these J-level variables. So invariably what happens is if you want to estimate the effect of J-level variables on Y, you've got to throw away the dummies, okay? But if you throw away the dummies, you're making the assumption that there's nothing in UJ that correlates with X. Now, if you are God, and if you know all the variables that makes leaders different and affects their level of Y, then good for you. Put them all in there and run the model. But you're taking the risk that there's going to be endogeneity. And I'm going to show you how we can test for that. Okay. So, the random effects approach has one advantage, but it's not really an advantage because I'm going to show you how we can do this in the fixed effect. The random effects approach allows you to put Z level variables in there. So imagine we're measuring leaders over time. So we could include here the leader's sex, the leader's age, the leader's big five, the leader's IQ. So these are constant over time. They don't vary. And we can include them in the model. But we can only include these things in the random effects model. We cannot include them in the fixed effects model because the fixed effects model is going to be completely collinear with these Z variables, okay? So Z level variables do not vary within clusters. Now you need to include everything in Z that matters so that UJ is not correlated to X. We want this covariance to equal 0. So it will only equal 0 if you measure everything that varies between leaders that matters. Now, how do you know everything? It's very hard to know. And this is where econometrics is very useful, because if you don't include all level 2 variables in the model, UJ will correlate with the level 1 regressors and you will have endogeneity. So in estimating these models, management researchers often center X in some way, cluster mean or grand mean centering. So the only valid method to center is cluster mean. And I'm going to show you why. And I'm going to show you actually that it's actually not even necessary to do it, because if we use another approach, we always get good estimates. So I'm going to show you that in a minute. Okay, so the model that I'm going to show you to use is the Mundlack approach. So he published a paper in 1978 in Econometrica, and he proved how we can model random effects models in a way that they are always consistent and don't have an endogeneity problem. So this is called the correlated random effects model. That's just the name for it. And basically what it does, it includes an extra variable here. It takes the cluster means of any regressors and includes them in the model. Okay, so it still has a UJ term, but what it does is it takes the average of every leader's X and includes it in the model. Okay, so there are two forms of this model. The first form gives gamma 2, which is called the contextual effect. And that's if X is not cluster mean centered. If you cluster mean center X, then you get what's called the between effect. Okay, so I define between and contextual effect over here. Basically, we don't really care about these things. It's in very specific situations we care about them. What we normally care about is gamma 1. And this gamma 1 is going to equal this gamma 1 no matter what you do over here. Okay, and here's the other advantage. When you use this estimator, you can still include Z level variables in the model. So this estimator does not use dummy variables. It uses cluster means, X bar. And because we're using cluster means, we can include any Z level variables in the model. All right, let me just stop there for a moment and see if there is a question. So I'm just defining models right now. I haven't shown you why one is better than the other. I'm just making definitions clear and terminology clear. So is there Is there something that's unclear, especially if you used HLM in the past and you're not sure about what I've said? Anybody?
I'm just trying to wrap my head around everything.
Yeah. Anyone who's used HLM and who is unsure about what I've said so far in terms of the terminology? Okay, so if that's not, there's no issue, we'll continue with the slides. So we can actually test the random effects assumption. So the random effects assumption, again, is does U correlate with X? Okay, we can actually test this assumption. Now, if you use the correlated random effects model, you automatically deal with this problem. Okay, I'm going to show you how. If you don't use this approach, then you may have a problem. So there are several tests that we can use. They are called, in general, Hausman endogeneity tests. And there are three ways to do this. One is the standard Hausman test. We do not recommend it because it does not work when you use robust or what's called cluster robust standard errors. The second approach is a likelihood ratio test, but it can only be used if you estimate it with maximum likelihood. Okay. The third approach is what we recommend, and also Jeff Woolridge and also McNeish and also Bleeser, we all recommend the Wald or F test because this is the most general test. It's always defined. It always returns a valid test for you, no matter how you have estimated the variance. And it's very easy to get this test. Basically, this test is simply, let me just go back one page. The endogeneity test is whether gamma 2 equals 0. So this is the F test on page 16. Is gamma 2 equal to 0? If gamma 2 is not equal to 0, if gamma 2 has a p-value less than 0.1 or 0.5, it means you potentially have endogeneity in the model and you must leave these variables in the model. Okay, so if gamma 2 is significant, it means you must leave x bar j in the model, because if you don't, you will have endogeneity. So this is the F test that we care about, and I'm going to show you how to do it, and I have a data set also for you to explain it. Okay, so in all cases we use the F test. It always returns a valid statistic. So let me show you how the data are usually set up when we do multi-level models. The data are usually in the long format. It means that we have leaders going from 1 to leader k, and they are repeated several times, either time measurement or a hierarchical panel. Could be subordinate 1, subordinate 2, or measured at time 1, time 2. So we observe y over time, or within the panel we observe x, and here we have a z level variable. It could be leader sex, 0 female, 1 male. Okay, so this is x bar, the cluster mean. So if we take the average of these two, we get 4.09. If we cluster mean center x, it means we take x, we subtract the mean from it. So 388 minus 409 equals this. 431 minus 409 equals this. So this is cluster mean centered. This is grand mean centered. So the grand mean is 252. So 388 minus 252 gives you 136. 431 minus 252 gives you 179. So that's grand mean centered. And then if we're going to use the econometrics approach with dummy variables, we have 6 leaders, so we need 5 dummy variables to identify them. So leader 1 serves as the base. When all the dummies are 0, it indicates leader 1. When dummy 1 is 1, it indicates leader 2. When dummy 2 is 1, it indicates leader 3, and so on and so forth. So this is how the data are set up in the long format. So does everyone understand what is in here and what the difference is between X cluster, X mean centered, X grand mean centered. Because I'm going to use these terms later on. So does everyone see where these things are coming from? I'll just leave you just 1 minute just to make sure that you all understand, or unless there's a question. Is everything clear? Okay, thank you, Laurent. Okay, so this is all very simple. If you've done HLM models in the past, this is exactly what you've done. The only difference is that you have not worked with dummy variables. I'm just putting them there so you can see what's going on. Notice that the dummy variables are completely collinear with Z. Okay, I cannot include Z in the model and the dummies because they are perfectly collinear. Okay, so if I include the dummies, I can't put Z. If I want to put the dummies, I just cannot put Z. If I want to put Z, I have to throw away the dummies. I can't have both of them. Okay, so the first thing I'm going to do is I'm going to demonstrate for you the econometrics approach, which includes fixed effects or correlated random effects. And then I'm going to show you the typical HLM approach, and then you can tell me what you observe in these estimators. So bear in mind 2 parameters. The effect of X on Y is 0.5, and the effect on Z on Y is minus 0.5. So you just have to remember these 2 things. So what we're going to do next is I generated the data. You have the data on Excel, so you can re-estimate these models in HLM, in SPSS, even in Excel, to see that you get the same variables as I do. But what I've done is I've created endogeneity in that Z is correlating with U and Z is correlating with X. Okay, now, just like I showed you yesterday and where Jason challenged me on, I'm going to show you the following. Whether or not you have endogeneity, the econometrics approach always works. If you have endogeneity and you use the typical methods that are used in HLM, you take the risk of having an endogeneity problem. Okay, so I generated the data with UJ correlating with Z and X. It's most of the time you're going to observe this correlation. It's extremely unusual that there's something in J that is not correlated with X or Z. It's extremely unusual. In real data, most of the time, UJ is going to correlate with X and Y. And if it does, you have an endogeneity problem. Okay? Now, you have the data. It's in OT panel XLS. And I'm going to show you a series of results. I'm going to re-estimate everything in Excel just to show you that actually OLS can do this. All right. So let's begin. And we're going to use OLS and we're going to estimate it in the wrong way. So this is OLS, which is ignoring completely everything. And look what we get. We get a very wrong estimate with OLS. Now I'm going to show you we can get a correct estimate in OLS, but using different setups. Okay, OLS can get the right coefficient. Now, if we just throw the data in OLS and we just run a simple regression, so let me share my screen over here. One second. Oh, sorry, not this version of Starter. I have 3 versions of Starter running. I've just got to clear this and exit it, and then share screen. And here we go. All right. So here is the data that I have. And And if you see on, if you see over here, I showed you that OLS, just a normal OLS, does not get the right estimate. So let me show you this. If we were to do this model in OLS, so we're going to regress Y on X and Z, or just Y on X, and you see we get two very wrong estimates. It's supposed to be 0.5. Okay. Now, why is it that we have very wrong estimates? Well, we have very wrong estimates because we've ignored the UJ term. Now, if we run the model and we include dummy variables, we get the correct estimate, which is 0.51. So if we were to use this in Starter, we would simply specify regress Y on X. And then I'm going to put I.lead N. So what Starter's going to do here is it's going to create dummy variables for me. I'm going to then run the model with a cluster robust estimate of the variance. I'm going to explain what this does in a minute. Now, what's going to happen is that I have lots of leaders in here. So it's going to take a while for Starter to run it because it's going to have to put 500 dummy variables. Okay, 499 dummy variables because I have 500 leaders. Now notice here, I get the right estimate, but I've explicitly modeled dummy variables because the dummy variables are going to take out any differences in Y that are due to the leaders. So it explicitly models that. So notice that I get the right coefficient, 0.51. I get a significant t statistic, but this model has a lot of dummy variables in there. So it's inefficient both analytically and it's inefficient statistically because the standard errors will be slightly larger. Okay. But all I wanted to show you here is that we get the correct estimate. Now, in econometrics, we have, I'm going to just switch back to Starter. And again, this you can do it in R very easily. I'm going to set up the data now in panel format like you would in HLM, for those of you who use HLM. And now all I'm going to do is I'm going to estimate this model using what's called the fixed effects estimator. And you look at that, Starter instantly gives me a result. It doesn't use dummy variables, and it gives me the correct estimate. Okay. T-statistic, and this model now doesn't have any dummy variables, but it gives me the right model. Now, if I try to put Z in here, look what happens. It throws away Z. You see that? It's saying I can't estimate the model with Z. It's omitted. Why? Because it's completely collinear with the model that I have, which is the fixed effects model. So if you use fixed effects and use the typical what's called GLS estimator, you cannot put Z in the model. Okay. So let me just stop for a moment because I think there may be a question. Okay, no question. So let me just stop for a moment and just show you what I've done here, if there are any questions about the first three models. So if it's green, it means it's good. If it's red, it means it's bad. Huh? Okay, so everything's perfectly clear, I hope. Now, let me show you what happens when we estimate the model in OLS and we include the cluster means in there. Okay, so we're going to go back to the OLS model. And now what we're going to do is we're going to put the cluster means in the model. So this is pure OLS, okay? You see that? We get 0.51 for X. Now, this T statistic is going to be incorrect. What we normally should do is use a cluster robust estimate of the variance. You can do this by hand if you want to. You just have to estimate the interclass correlation coefficient, and you can make these adjustments by hand. It's not difficult to do. Whoever wants, I can give you these formulas. HLM does this automatically. If you use maximum likelihood, it does it automatically. But notice that we get the right coefficient. Now, let me share Excel with you, and I'm going to put the data in Excel. So let me open up the data set for panel, and I'm going to show you that Excel can do this for you as well. Okay, so let's share my screen in Excel. 1 second, I just got to find the. Okay, so I have the data in Excel. I'm just going to rearrange it quickly just to put Y by itself. And I'm going to just move Z to the right side so that we have, okay. So I'm going to go to data. I'm going to go to data analysis. And I'm going to use regression. And I'm going to say Y variable is here. I'm going to put it in Excel. And I'm going to put the two X variables, X and the cluster mean of X. And I'm going to run the regression. And look what I get. There was a, sorry, did I make an error here? Excuse me, sorry, I think I made a mistake. It gave me some error. Hold on a second, let me just run it again. I just have to go to data analysis, regression. Sorry, I think I made a mistake. So this is Y. I should have taken away. Oh, labels, I have labels in there. Yeah, that's correct. So I have to put the Y as the label in there. Let's just go back to the top. Okay, so Y is in there. And then the X variables, we need to put X and X cluster. And now we run it. So look what we get. We get 0.51 for the coefficient of X on Y. So this is now Excel. This is using Excel, which is using the function of regression. So I just want to show you that, you know, and we got a T statistic of 13. I told you that requires correction. So, you know, if anyone tells you that you can't estimate multi-level models in OLS, say to them, it's not true. If you include the cluster means in there, you get exactly the same effects that I've shown you here. The only difference is you need to correct the T statistic, and there are formulas to do that by hand. It's very, very simple. All right. Now here's the other thing. Yeah. Is there a question? Did someone open their microphone? No. Okay. Here's the other thing. We can estimate this in OLS and include Z now. And we will still get the correct coefficient. It's supposed to be -50. But let's go back to sharing the screen in Excel, just so I can show you that it's possible to do it in Excel. Anyone who's told you the contrary, that you can't do this in Excel, has not spoken correctly. So Y is in there, and now the X variables, I'm going to include X, X cluster, and Z, and I'm going to run the regression. Notice Z is -46 and X is +41. -46 + 41. Let's go back to see what Starter had given us. minus 46 point something 47 and plus 51. So all these models are perfectly well estimated in OLS or with GLS. And the problem is, though, when we estimate them using random effects and we don't model the cluster means. Now, if you used HLM, the typical HLM estimator, which is here, so I'm just going to write HLM, depending on which estimator you use. You can use maximum likelihood or restricted maximum likelihood or GLS. If you include the cluster mean in there, you get very good estimates. You see that? 0.51, 0.47 for Z. If you cluster mean center X, you still get a good estimate. Okay, the only difference now is that here we have the between effect, and this is the contextual effect for these two variables, as I showed you before. So HLM can give correct estimates in the model. The problem is when you use HLM and you don't include X bar. So if X bar is omitted, look what happens. The X coefficient, instead of being 0.51, is now 123. Instead of this being minus 51, it's minus 33. Now, if we cluster mean center, we do get good estimates for X, but we get really bad estimates for Z. You see that? If we grand mean center, this is grand mean, we get bad estimates for Z, bad estimates, pardon me, for X, and still bad estimates for Z. So the only estimator that works is the estimator where we include the cluster means. Whether or not we include Z is irrelevant. Let's just go back one slide, and then I'll let you digest that. Notice, here I don't include Z, and I get a good estimate. I don't include Z, I get a good estimate. I don't include Z, I get a good estimate. Okay? I include Z, I get a good estimate. I get the same estimate every single time, whatever I do. As long as I use dummy variables, as long as I use the fixed effects estimator, or as long as I include the cluster means, I can have my cake and I can eat it too. En français, on dit on peut avoir le beurre et l'argent du beurre. I think. Is that correct, Laurent? You can have your cake and eat it too.
Yeah, I don't know the French equivalent, sorry.
Mais tu peux avoir le beurre et l'argent du beurre. C'est-à-dire, tu peux vendre le beurre, garder le beurre et prendre le fric du beurre. Voilà. Okay, so let me stop here for a moment. You have the data, stick it in SPSS, stick it in R, stick it in HLM, and see if you can get the same estimates as I do. If you want, you can do it now, or you can do it afterwards. Now, all this could be a fluke, huh? And as Jason knows, who does simulations, I could have picked one simulation that gives all right results for my estimators and bad for the other ones. Huh? I could have done this expressly just to trick you. So this was not a fluke. And what we're going to do is we're going to do a simulation with millions of models so I can show you this was not a fluke. In fact, analytically, mathematically, I can prove to you that this estimator is consistent. So we know this is not a fluke. But let me just stop here for a moment and see if there are any questions. So,
John, I have a question. This is Joe Schmitz.
Hi, Joe.
So my limited understanding of econometrics is that fixed effects modeling is appropriate if you have time invariant unobserved variables. So if you're doing some type of time series analysis and your endogeneity did vary over time, could you apply, like I think leg dependent variable modeling is sort of appropriate for that. Could you do a similar approach with like legged cluster means in hierarchical models?
No. So what you're talking about, I guess, is the Arellano bond estimator. So in econometrics, fixed effect says the following. if we measure x, j over time 1, time 2, time 3, and then, you know, we measure y and we measure some things, we can take out the fixed effects by using dummies, as I just showed you. So one approach is that we have data over time. So this is called a panel model. So where we have J is measured over time, but we can also have J that's measured hierarchically. This is called a pseudo panel. Okay. And again, whether we have hierarchical data going up and down or time over, if we measure something over time, we can use fixed effects in both of these models. It's the same kind of model. This is called a panel model, and this is called a pseudo panel model. Now, this is not to be confused with including lags of variables. This is something completely different. And depending on how it's set up, we can set up what's called an Arellano bond estimator, which can take out some forms of endogeneity with lags. But we're not talking about lags here. I don't know if that answered your question.
Okay, yeah, thank you.
Okay, so nothing.
I'll do some more investigation. Yeah.
Okay, so there are other models where we can use lags and we can do certain econometrics with lags, but these are not the models I'm talking about over here. Okay, these are just simple panel models, either over time or hierarchically. Subordinates nested under the leader. I have 3 subordinates nested under the leader, or I measure the leader over time.
Yeah, okay, thank you.
Welcome. Any other questions before I show you the simulation results?
John, Laurent here. Can you give us, or give me, a quick review as to what the dummy variables are doing?
Mm-hmm.
What is their purpose in the model? What are they doing? And by not including them, what are we losing?
Okay, so the dummy variables are going to capture any differences in y on the intercept. Okay, so you know every leader has a different intercept. So we have, maybe this is leader 1, this is leader 2, this is leader 3, this is leader 4, and imagine we're measuring, this is the y and x, and imagine the slopes are the same for everybody, but the intercepts are different. Now, why are the intercepts different? We don't know. But if we include the dummy variables in there, it accounts for the differences in intercepts. It explicitly models the intercepts for every leader. If we don't put the dummy variables, it assumes that these intercepts are random. Okay? And that there's no correlation between these intercepts and between these values and x. Right. So that's the difference. Okay. And when we include, here's the funny thing. Let me just quickly show you something very, very interesting, Laurent. I'm gonna just quickly open up my starter again, and I'm gonna show you what the cluster means do.
And just as a reminder, the Z variable, that is something about the leader.
Yeah, at the leader level, that's invariant over time. Okay. Now, here's the code, Laurent, that is used to generate the data that I gave you. Okay. Now, what I'm going to do is I'm going to set this asymptotically. I'm going to put, instead of 500 leaders, I'm going to put 10,000 leaders. I'm doing this on purpose. I'm just going to show you something interesting. And instead of, say, 10 subordinates, I'm going to put 50. All right. Mm-hmm. So we're going to have a massive amount of data in here. The reason why I'm doing it is I want to show you that the fixed effect, which is in line 9, you see I generated a variable called A, and A affects both Z, and A affects X as well. So I'm creating endogeneity due to this omitted common shock UJ. And now what we're going to do is we're going to create cluster means. Sorry. Yeah, I just need to do this again. I just want to show you something that's going to freak you out. Okay.
And again, cluster means is the mean of the X variable for each leader.
Exactly. Now, think about this, Laurent. If each leader is different and has something common to them, and if I take the average of X for every leader, what am I essentially doing? This is not a trick question.
What are you doing by averaging X for each leader?
Yes. What am I capturing by averaging X in each leader? And I'll give you a hint. I'll show you the correlation matrix here. Look at the correlation between A, the fixed effect, and the cluster mean.
Give me an example of X. Give me an example of what X can be.
Can be anything. The charisma of a leader.
Right. Okay.
Yeah. Now, if there's something common in the speeches of the leader that is due to the leader's intelligence or sex or anything, if I take the average of those scores, it should approximate the fixed effect very well. So look at the correlation between A and the cluster of X. It's 0.99. Okay.
Mm-hmm.
Now I'm going to even take it bigger. I'm going to add a couple more million observations just to show you that asymptotically, what I'm saying is correct. Okay. So in asymptotic space, if we gathered a million zillion data points, or we did simulations with sample of 500 leaders repeatedly, we will get exactly the same result. Okay, so I'm gonna take the cluster mean as well. Just 1 second, because I have a zillion million data points here. So Starter is taking its time.
Mm-hmm.
Okay, it's done it. Now I'm gonna generate the cluster means. Okay, it's doing it by sort leader n generate. It's going to take a minute. Let me just stop sharing so it just goes faster. So if you look at the data I sent you in Excel, the cluster mean is standing in for A. And if you generate data with an unobserved common shock, it's going to correlate 0.90 something with A. Okay, that's how it's going to be. Because if there's anything common to X, that thing that's common, if we take the average of it, it should approximate perfectly well the unobserved fixed effect. So that's what the dummies are doing. Yeah. The dummies are saying, look, there's something common in the leader. Let's model that explicitly, because that's what makes leaders higher or lower on Y. Let's model that explicitly with dummy variables. An alternative way to do this is, let's take the average of all the X's and measure that as a cluster mean. One way or another will give you exactly the same result.
Right, so it's one or the other.
Yeah, it's one or the other. And the most efficient way to do it is the cluster mean. Okay. Right. Starter is still working because I have 99 million observations that are expanded 100 times. So we're going to have 9.9 billion observations. It's still working. So let me continue. When it works, we'll come back to that. Okay.
Mm-hmm.
Let me just show you the simulation that we did. All right. So the idea is that AJ, the unobserved fixed effect, is going to correlate completely with the cluster mean. This actually is AJ. So Laurent, if you had two X variables, X1 and X2, you need to take the cluster means of X1 and X2, and the cluster means of X1 and X2 will equal to AJ, which is the fixed effect. In other words, going back here, these cluster means, this we can get from the cluster means or the dummy variables. And I recommend that you use the cluster means. It's much more efficient. It's more flexible. And when we do the cluster means, we can actually add Z variables in here as well. Okay. Is that clear, Laurent?
Yeah, it helps somewhat. Yeah.
Okay, I'll come back to that. Let me just let me wait until Starter has finished generating the data. So the idea is the following: the fixed effect uj, if it is uncorrelated to x, you may as well leave it here, but you don't know if it's correlated to x. You can test for that by moving it in here with cluster means of all the x variables. When it's moved in here, is AJ allowed to correlate with x? Yes or no?
Is AJ allowed to correlate with X?
Yeah. Yeah. So we have a model here that Y depends on X and A. Yeah.
For sure.
Now we allow the correlation, correct?
Yeah.
So we account for possible correlation between
a fixed
effect and X. So you see, we don't make that assumption that it's orthogonal. Here,
right.
It's assuming that it's orthogonal. Here, it's not. So this is what dummy variables do. Dummy variables move uj in the fixed part of the model and model it as dummies, or we can include the cluster means. All right. Yeah. And this is the way we avoid making an assumption that's untenable. That's it. It's that simple. It's so simple that it's almost deceptively simple. It's like, what? How is it so simple? That's all it's doing. The cluster means account for between leader differences in X, which affect Y. That's it.
Does it become dramatically more complicated when we have, because what we have here is a model where we're trying to regress a level 1 outcome onto a level 2 predictor.
Yes.
Right? What happens when you're also including level 1 predictors and there's potential collinearity, not collinearity, but endogeneity there?
This is level 1. This is level 1. This is level 2. So here it's an effect of level 1 on level 1. Level 2 is when we want to do the next thing, Laurent. Let me just turn the page. Here. Now we have level 1, level 1. So whenever it's ij, it's level 1. Whenever it's j, it's level 2.
Mm-hmm.
Okay. So if we want to include level 2 variable in here, we can do that. We can do that when we include cluster means. So if we just turn the page to the little simulation I showed you, look. You see here, we have level 2, level 1. And here we include the cluster mean, level 2. So usually we are interested in this effect here. Sometimes we're interested in level 2 effects. But if you're interested in level 2 effects, you better add in the cluster means. Because if you haven't measured every level 2 variable that matters, then you face an endogeneity problem. Because whatever you haven't measured in the model goes in uj. If uj correlates with x, you're going to have an endogeneity problem, which is evident in the next estimate I'm going to show you. 1 second, let's turn the page. Look here. So here, this is using HLM. Okay, all these models here, whatever is RE are the typical random effects models of HLM. Okay, now if you set it up the right way and include the cluster means, everything's good. See, when the cluster means are in the model, all is good. Or if you cluster mean center, all is good. But when you cluster mean center, Z goes crazy. You see that? If you don't include the cluster means, you see, if I include cluster means in here, Laurent, Z is, I get a good estimate for Z. You see that? Z is good, Z is good, Z is good. Z is not good over here, and Z is not good over here when I don't include the cluster means.
Okay.
So what's the moral of the story?
Are you asking me or are you telling me?
I'm asking you.
Include cluster means.
That's it. It's that it. Now, let's switch. Starter just finished. We have a zillion, million, billion data points here. Now, Laurent, I want to freak you out. So we generated A, which is a random normal variable at the Z level, at the J level. We generated Z, which depends on A and some disturbance. We generated X, which depends on the fixed effect. We generated Y that depends on X, on Z, and on the fixed effect. And then I said to you, asymptotically, the cluster mean should correlate perfectly with A. Let's look at this now and see what we get. Sorry, this correlation might take a while to calculate because it's so massive, this data set. Now, if it's not 0.9999, I will eat my hat, okay? And you should fire me because I'm a very bad professor. Okay, please hurry up, starter.
You have a couple of comments, questions in the chat, John,
okay.
if there's some time.
Yeah, let's go while it's calculating. So I see here, the dummies would capture the cluster means, right? Jason, that's correct. Jason, Hayes and his grad student did something similar when looking at two condition measures with mediation models. Montoya, Hayes, two condition. Okay, I don't know what they did there, but I believe you, Jason. If they did cluster mean centered X, then they have a good estimate for X, but they won't have a good estimate for Z, as I've shown you. So mean centering X doesn't really help. It only helps if you put the cluster means inside as well, especially if you have Z level variables. So Hamza, so we include Xij cluster mean and cluster mean centered in the model, just to make sure. Hamza, you don't need to cluster mean center X. You can if you want to, but you don't have to. Okay?
Thank you. Thank you.
If you put it in, then the gamma, let me just share my screen. Hold on a second. By the way, it's finished. So we have here 100 million observations. Laurent, look at the correlation.
Yeah, I guess you don't have to eat your hat.
It's 1. If we round it up, it's 1, correct?
Yeah.
Okay. So you see, the cluster means stand in for UJ, which is unobserved. Okay. Now, I showed you what UJ is. I called it A in my data set, and I showed you that X, the cluster mean, correlates perfectly well with unobserved effect. Let's go back to Hamza's question. If you cluster mean center, you estimate the between effect with gamma 2. If you don't cluster mean center, you estimate what's called the contextual effect. I define them over here, and it's in the paper. We give examples. Okay. Let's go back here. If you cluster mean center, you see how this changes. Instead of being 458, it becomes 509. You see that? So here we used cluster mean centered. We get a good coefficient, but that gamma 2 changes, and everything else is exactly the same. So do you need to cluster mean center? No, you don't need to do any centering. Grand mean centering, by the way, is evil, as you all see over here. Yet about 20% of the articles in the management literature, grand mean centered. Okay, so let me finish up. I'll quickly show you the simulation because we have 20 minutes, and then I'll take some questions. And by the way, my daughter is here tonight, so I don't have to fetch her, so I'm happy to stay till 6:30 without being stressed, in case there are more questions. All right. So, like I said, this all could be a fluke. Oh, wait, sorry, someone has a question. Duke, if I understand correctly, CRE models solve for level 2 endogeneity. They solve for unobserved fixed effect endogeneity. They may correlate with the level 1. That's correct. Duke says again, perhaps they would involve including instrumental variables at level 1. So if the level 1 variable or the level 2 variable are endogenous for a reason other than the fixed effect, then you need to use instrumental variables. That's correct. Then you need to use what's called a fixed effect a panel estimator with instrumental variables. So it's basically fusing what we did today with what we did yesterday. So if you have an endogeneity problem for other reasons, then you need to include instrumental variables. But in most cases with panel models of this sort, usually the fixed effects estimator deals with it, or the correlated random effects estimator deals with it. Okay, so all this could be a fluke. And those of you who do simulations, you know, you don't just show one simulated data set because the estimates could go all over the place. So what we're going to do is we're going to do a massive Monte Carlo. We did this massive Monte Carlo because the reviewers at ORM simply did not believe what we said. We had one reviewer coming back saying, you guys don't know what you're talking about. We've been estimating HLM models for all our lives. OLS can't do this. And what you're saying is hocus pocus econometrics. So the editor said, okay, why don't you do a massive simulation and let's see what happens. So we did a massive simulation. How massive? Well, you will see. We have two level 1 variables, x1 and x2. We have two level 2 variables, z1 and z2. And we are going to see how this estimated model pans out when we use different derivations of the model. We're going to vary gamma 1 and gamma 3 from -2 to 2 at increments of 1. Okay, so we're not holding it constant. When it's -2, it better be -2 when in model recovery. So we're gonna fully cross and manipulate gamma 1 and gamma 3. And we're going to hold constant gamma 2 and gamma 4 at -1. Then we're going to hold constant the correlation of x1 and x2 to 0.3. We're going to assume z1 and z2 are uncorrelated. Now, these assumptions here, we can relax them. It makes no difference. And we showed that to the editor. We just didn't want to waste computing time because we used a massive computing cluster. You will see why. So, level size at sample 2 was varied from 20 to 1,000. So why did we do that? We were informed by our review, and we took a random sample of papers, and on average the sample size at level 2 was about 50 to 60, something like that. So we're gonna manipulate across all sample sizes at level 1, and we're gonna manipulate at level at level 2 sample sizes, and level 1 we're gonna manipulate from 2 all the way to 40. So we're going to have to 30, pardon me. So we're going to have a minimum of 40 observations and a maximum of 30,000 observations. We're going to manipulate the shock between UJ and level 1 variables to be 0.1, 0.3, or 0.50. So this is manipulating how strongly correlated the fixed effect is with X. And in one condition, we will have a strictly exogenous Z1 and Z2 when the correlation is 0, and then we're going to have two conditions where there's a correlation between Z and the fixed effect, and we're going to affect the ICCs such that they range from 0.85 all the way to 0.885. So the ICC is the intercluster correlation. So we have really a lot of manipulations, which means we have 20,250 different models, each replicated 1,000 times. So we have 20 million observations, 20 million different data sets. I know this is a lot of data sets, and I know we set the bar very high for anyone wishing to do simulations from now on in ORM, but we had to do it because the reviewers simply didn't believe us. We had to run this in a physics cluster at Aalto University. It took a few hours, but we had dozens and dozens and dozens of computers. We're running on supercomputer basically. So let's see what happens to X1. Now, anytime you see CRE, that's the correlated random effects estimator. Okay. Notice that we don't ever have a problem with a correlated random effects estimator, nor do we have any problem when we cluster mean center and we want to estimate the effect of X1. Okay, so all the estimators are good, except we have a problem with random effects estimator. here, and here. So when it's grand mean centered, we have a problem, and I showed you that before. Or, and here it is as well, grand mean centered. You see that? In all cases, grand mean centering has a problem. It doesn't give you a good estimate for X1. You need massive sample sizes before it starts getting to 0. So this is the mean estimation error. We subtract the true coefficient from the estimated coefficient. Now, as the number of clusters goes to infinity, notice that when you grand mean center, you still have a problem. It doesn't react. The coefficient doesn't come down to 0 estimation error. Only the other estimators give us good estimates. Okay, so grand mean centering requires a massive amount of observations per cluster. Okay, it means that I need to measure John 30 times at least before I get a reasonably good estimate from grand mean centering. All right, let me just stop there for a moment and see if there are any questions. So, you know, these are observations per cluster. So in other words, how many observations I have per cluster, and this is number of clusters. So this is J, and this is how many observations I have at Xij. Interesting, huh?
Which is the reference for this, or which paper are you referring to?
0. I want 0. I want 0 estimation error.
No, I'm sorry. Which published paper is this discussed in?
In the ORM paper,
Okay.
Antonakis, Ronco, and Bastardos. Yeah.
Okay.
So we want 0 estimation error. And like I said, we manipulate the coefficients across a range. So, you know, gamma 1 and gamma 3 are manipulated from -2 to +2. So we know what the true model is. Then we estimate the model and we look at the difference, and that's what's captured in the mean estimation error. Okay, so the only models that work are the correlated random effects model and if you cluster mean center. Now I'm going to show you that cluster mean centering helps you for X, but it doesn't help you for Z. Okay, you're going to see that in a minute. So let's turn the page. Now, here is the mean estimation squared error. So this tells you how efficient your estimator is. So of course, as you have more and more and more observations per cluster, you want your estimator to be more and more and more efficient. So the squared error is the variance of the estimate. So you see all of these guys do a reasonably good job, except the 2 grand mean centering conditions. You see, they need bigger sample sizes before they get down to 0. And they don't react so quickly as the clusters, number of clusters are increased to infinity. You see, these guys go down much faster to 0 error, and they go much faster to 0 error. So grand mean centering is just really no good. Don't do it. Okay. But now, what about cluster mean centering? Because cluster mean centering so far has given us reasonably good estimations. Okay, you see, anything that's cluster mean centered has given us good estimations. It's all in here. So it's pretty good cluster mean centering for X, but it doesn't help for Z. And you're going to see that in the next slide. Okay, here's the problem now. Grand mean centering is bad. Grand mean centering is bad. Cluster mean centering is bad. So this is cluster mean, this is grand mean. So you see what happens. Cluster mean centering helps you for the X level variables, level 1, but it doesn't help you for level 2. The only thing that helps you and the only thing that works is the correlated random effects models. They are the ones that give you the least error and the least squared error. As you see, the least squared error, as you go to infinity, they start off at less error, and they get faster down to 0 than any of the other approaches, grand mean or cluster mean centering. So basically, the moral of the story is grand mean centering and cluster mean centering are pretty useless. If you want, you can cluster mean center, but if you do, include the cluster means as well. Sorry, something's happening here. Sorry. If you're going to cluster mean center, include the cluster means in the model. So in other words, always have the correlated random effects model. You see here, the brown model is cluster mean centered, and it's in here, it's good. It's in here, it's good. If you don't include the cluster means, you see the pink model? The pink model is no good. If you don't include the cluster means, the pink model is no good. So either you're going to have a problem of estimate consistency, you're going to get more error, or you're going to get more variance. So the bottom line is the best estimator is the correlated random effects estimator. Whether you cluster center or not is irrelevant. And just to show how the state of the art is in our field, we looked at the top 10 journals in applied psychology and management, and we took a random sample of articles, both micro and macro. So we had 204 articles, and we checked to see what they did. And overall, what we found is that about 50% of the articles actually used fixed effects or correlated random effects. So 1 out of 2 did it correct. But this is kind of biased because most of the correct articles were more macro articles. They were articles estimated usually by economists or people in strategy. In about 1 of 2 articles, either it used random effects and it was justified, but it was only in about 3% of cases. Most of the times it used random effects and unjustified the estimate. In other words, they never did a test to see whether the estimator was consistent. So here is the problem. 47% of articles used a random effect assumption and didn't justify it. This is a problem. Now, here's the other problem, that a lot of the articles did not have an exogenous X variable. 80% violated the usual endogeneity assumption. And this is, Laurent, your question and what you said here, they should have used an IV estimator, and they did not. So at the end of the day, only about 12% of the articles did it correct. They modeled correctly the random effect assumption, and they satisfied the usual exogeneity assumption, which is kind of sad. But anyway, at least 1 in 2 articles did test whether the random effects assumption held. So 10 years ago, we found that 80% of the papers we surveyed did not correct for this problem. And we found a very similar result now. So still, it seems insufficient training. Still, it seems people are using HLM or some program without really reflecting on it. And it's going to take a bit of time before people know about this. I just want to go to the references. I'm going to come back. So this already was proven in 1978 by Mundlek. McNeish rediscovered it. I rediscovered it in 2010. We rewrote this article in 2021 just to make everything more evident. Bleeser has rediscovered this. So, if you don't believe what I said, the editor of ORM is Bleeser, and he has a Journal of Management. He says exactly what I've just said here. McNeish and Kelly have said exactly what I've just said in Psychological Methods. What we did in the ORM article is we did a very, very extensive simulation to prove that what we said is correct, because the reviewers just couldn't believe what we said. Just to finish up, we have a little flow chart that helps you to decide what to do. At the end of the day, the correlated random effects model is always going to give you correct estimates, okay? Only use a random effects model if you show that you satisfy the random effects assumption. And that's going to be usually quite unreasonable assumption to make. So the bottom line is this: if you have panel data, if you have hierarchical panel data or panel data over time, just estimate the correlated random effects model, include the cluster means of all the X variables, and you should be fine. We have a little video on this if you're interested. And my co-author, Mikko Rönke, has a lot of little videos on his website that talks about this and other problems. So I invite you to take a look at that, because I think you might find this interesting. Okay, so let me stop there, and I'm happy to take any additional questions which you may have.
And thank you, John. Because we are close to the official time, I think people who want to ask questions can stick around. But I wanted to say an official thank you for sharing all of the information resources that I think are going to be useful to us for many years to come, as you say, as the trend shifts. So your time, your input is very much appreciated. So for anyone who does want to ask questions and stick around, thank you for making yourself available further too.
Yes. So thank you, AJ. And what lecture I gave today is quite technical. But if you have the time, if you read our article in ORM, if you play around with the data set I gave you and see for yourself that you can do this using any basic statistics program, then you will understand. I think the key insight to have here is what I showed you with Laurent, is that the cluster mean of X is a very good proxy for UJ. However you construct UJ, the cluster means will always take care of it, or dummy variables. But can you imagine the data set, Laurent, that I just gave you with 100 million observations? It would have taken Starter probably 3 days to estimate it with dummy variables. So if you use the cluster means, it just requires one vector. It's just one variable, boom, and it estimates it instantly. So once you understand that the cluster mean can replace UJ, if you include the cluster mean in the model, let me just write this out again, and then I'll take questions, AJ, I'm sorry. Sorry, let me just quickly share this. So if we regress Yij on beta 0 ij plus beta 1 of xij, and include in there beta 2 plus uj plus eij, by including the cluster mean x bar j, I ensure that the assumption I make with this is going to equal 0. I will actually satisfy the assumption that covariance xu is equal to 0. Only if I put xij, then this assumption will hold. If I don't put this in there, it's possible that uj will correlate with x, and then it's going to make beta 1 inconsistent. So that's basically the bottom line of what I wanted to explain to you today.
I'd like to remind everybody that this has been recorded. And so if anybody wants to revisit this, perhaps on half speed, then it will be at your disposal. Geneviève, if you're paying attention, perhaps not, if you could let everybody know what the link is to find the video eventually, that would be wonderful.
Yep, we'll be sending an email after today with the link to the recording.
Thank you, Geneviève. And if you did pay attention, Geneviève, you also will be able to recite the mantra, always include the cluster means. I must have said it 100 times, so now it's probably in your head as well. Okay.
Thanks.
Thank you.
Does anybody have any other questions?
Jason looks like he has a question. He really does. No? Come on, you must have maybe a little question. A teeny weeny little question.
No, well, I question all the work now that I've done is, I think, the thing.
Yeah, I'm really sorry, Jason. I'm the harbinger of bad news, but you know, you can go back, play with it, and you will see. if you have endogeneity or not, our estimator always works. It's like yesterday. It's exactly the same thing. And I know it's true because we can prove it mathematically. Now, what do you do if you've published a paper and you did HLM and you didn't check for this? Okay, great. I mean, it's done, it's finished. And just look forward. So, you know, people always sometimes lament, like I myself, I have a paper that I've denounced, my most cited paper in 2003 in LQ. I disagreed with myself, and I published another paper questioning what I did. One of the reviewers said to me in the third round in the Journal of Management, "You're going a bit too hard on Antonakis," not knowing that I was Antonakis critiquing myself in the past. Now, you know, whatever, you know, if you want, you can write a paper and update it. If you don't update it, who cares? You know, just look forward and see if we can get it right in the future. And I invite you to play around with these models. And anyone who's followed any of my seminars, I am very happy to engage with you after the workshop and answer any questions you may have. Of course, I'm not going to do it for you. Take the time to read. And then if you have a model, estimate it, send me the output and say, did I do it right? And I will tell you. I'll be very happy to help.
Okay, thank you.
Yeah, I feel very, very strongly about this. And, you know, I hope I don't come across as a bit conceited in my teaching approach, but you know, we can test everything. We can look at the mathematics. I know for a fact that the estimator that Mundlach proved in Econometrica in '79 is correct, because it's been reproven and rediscovered multiple times. Yeah, and there's nothing wrong with the HLM estimator if the assumptions of the estimator are met. There's nothing wrong with it. But if they are not met, then you have an endogeneity problem. And 99% of the time, one will have an endogeneity problem because it's extremely unreasonable to assume that if I measure John over time, that there's nothing in common that John has that may correlate with X and Y over time. And if you think that you know all the variables that matter, I think it's really conceited to assume that one knows all the Z variables that one has to include. You miss out one, you'll have endogeneity. So yeah, you can input sex, you can put age, you can put the big five, you can put IQ, put also the cluster means of X, and then you know you're safe. Whatever happens, you're safe. Thank you.
John, there was a question from Kautar.
Yes.
I answered, but please verify my answer.
Yes, sir. Sorry, I need to put on my glasses because it's quite little. Thank you. Very helpful and informative. Thank you so much, John and organizers. What? Not that one. Oh, excuse me. Does a moderating variable have the same potential endogeneity problem as a mediating variable? Yes, it does. It has the same potential problem because if Z is a moderator, and you interact Z1 with Z2, you still need to include the cluster means of all Xij variables and include the interaction of Z with X and Z and the cluster means. Yes. And who answered the question? Laurent. Yes. Thank you, Laurent. Laurent, you can easily replace me now in the future on this workshop.
Yeah, I don't think so, man.
No, but you answered every question perfectly well, and I put you on the hot seat when I asked you what AJ stands for with a cluster mean, and you answered correctly.
I can't even remember what that answer was. But anyways, thank you very much, John. This was, especially given the fact that it's been video recorded, I think it's going to be just terribly useful for us as a school, as an institution, and whomever was able to join us from outside of the University of Ottawa family. Yes, so is there, AJ, was there any final thoughts you wanted to share?
No, so, I mean, same as you said, just that I think that we'll be referring back to this many, many times and the papers. So look forward to citing you and being trained by you again.